Welcome to today's Explainer. Look, if you're like most people, the word logarithms probably triggers some mild panic, right? It just brings up memories of frustrating algebraic chores, or maybe it's just that random confusing button on your calculator. Well, let's fix that right now. Over the next few minutes, we're going to take a calm, unhurried journey to shift that perspective entirely. We're going to discover how logarithms are actually a fascinating tool that beautifully describes the reality around us, literally everything from the history of human survival to the hidden source code of nature itself. Okay, so let's dive into this by taking a little trip back in time. I want you to imagine being a sailor in the 1600s. You're trying to set a course across the English Channel from Dover to Dunkirk. Now, to figure out the correct angle for your ship's compass, you are absolutely drowning in tedious, error-prone manual arithmetic. I mean, you're dealing with massive numbers, working out complex long division by candlelight on a rocking ship, and obviously, there is no electronic calculator in sight. Out there, a single arithmetic mistake could literally cost you your life. But then a life-saving solution comes along. In 1614, a Scottish mathematician named John Napier publishes his logarithm tables, basically inventing a completely new set of numbers. 10 years later, Briggs refines this into base 10. By the 1630s, this sparks the era of the slide rule. These printed tables and the physical slide rules they inspired became the absolute most powerful computing instruments on the planet. By just physically sliding rollers marked with logarithmic scales, engineers could suddenly calculate complex geometry in seconds. This completely dominated human engineering and science for over 350 years, right up until cheap electronic calculators finally arrived in the 1970s. To really understand why this was such a game changer, think about that sailor's math problem. If a navigator needed to divide distances to find a course, let's say dividing 5.61 by 46.6, doing that long division manually was a total nightmare. But Napier's tables offered this brilliant shortcut. Instead of dividing those ugly numbers, the sailor could just look them up in a printed table, find their logarithms, and simply subtract them. Section 1. The mathematical wormhole. Turning complex problems into simple ones. So, the absolutely crucial starting point here is understanding what a logarithm actually is. In the simplest possible terms, a logarithm is really just a tracking tool. It counts how many times you multiply a base number together. Fundamentally, you can think of a logarithm as just a number that desperately wants to be an exponent. It's asking one very simple question. Hey, what power do I need to raise my base to in order to get this specific number? Look closely at this table here, which uses a base of 2. If you want to multiply 2 times 4 to get 8, you don't actually have to do the multiplication. You just step into the wormhole. Look at their logarithms on the right, which are 1 and 2. Simply add those together to get 3. Now step back out of the wormhole. The logarithm 3 corresponds exactly to the number 8 on the left. It's almost like magic. Complex multiplication becomes basic, simple addition, and it turns messy division into simple subtraction. If we calmly look at this, we see there are really just 3 distinct ways to write the exact same relationship between a base, an exponent, and a final number. We can write 10 to the third power equals 1,000. We can ask for the cube root of 1,000, which gets us back to 10, or we can use a logarithm. Log base 10 of 1,000 equals 3. You see, it's really just a change in syntax. So whenever you're faced with a logarithm in the wild, don't let the strange spelling or the sudden appearance of letters in your math problem intimidate you. Just sit back, take a breath, and remember this simple mantra. It just wants to be an exponent. It is merely asking you what the exponent is. That's the whole shebang. Now, here's a fun fact. Napier originally used an incredibly clunky base for his tables, the number 0.9999999. I mean, mathematically interesting, sure, but a total headache to actually use. Well, a professor named Henry Briggs realized this, traveled to meet Napier, and convinced him to switch to base 10. And wow, this changed everything. By using base 10, the logarithm simply counted the number of zeros in our decimal system. Log 100 is 2, log 1,000 is 3. Since counting zeros is exactly how our human brains naturally prefer to do math, this was a massive, immediate relief for everyday arithmetic. Section 2. Measuring the real world. Earthquakes, viruses, and human senses. Okay, let's move to how these abstract mathematical wormholes actually mirror the physical patterns embedded within our real world. Consider how we measure massive events, like earthquakes, on the Richter scale. The Richter scale is a logarithmic scale. When you hear on the news that an earthquake went from a magnitude 4 to a magnitude 5, it sounds like a tiny single additive step, right? But in physical reality, it represents a massive multiplicative jump in energy. A magnitude 4 is roughly equivalent to 1 kiloton of TNT. A magnitude 5? That grows by a factor of 32. It's the equivalent of a 32 kiloton nuclear bomb, like the one dropped on Nagasaki. This chart brilliantly illustrates how a logarithmic scale solves a massive visualization problem for us. It allows humans to squish hugely varying sizes onto one simple, readable graph. Without it, trying to plot an earthquake the size of a hand grenade on the exact same piece of paper as a city-destroying megaton-level event would be completely impossible. The logarithm scales it down so our human brains can easily wrap our heads around it. But, it's not just earthquakes and viruses that act logarithmically. Our own bodies do too. Let's try a quick thought experiment. If you ask a young child, maybe a 5-year-old, what number is exactly halfway between 1 and 9, what do you think they will naturally say? Well, as educated adults, we've been trained to think linearly. We add equal steps, so we instantly say 5 is exactly halfway between 1 and 9. But anthropologists have found that young children, and even cultures without formal counting systems, will instinctively say 3. Why? Because of a principle in psychology called Weber's Law. It states that humans naturally perceive changes in stimuli, like the passing of time, the pitch of a sound, or the distance between numbers, logarithmically. To get from 1 to 3, you multiply by 3. And to get from 3 to 9, you multiply by 3 again. Our brains actually natively perceive the changing world through multiplicative growth, not linear addition. Section 3. Discovering Euler's number, the mathematics of compound interest. Now, what's really interesting here is how we journey from measuring the outside world to discovering the ultimate natural rate of continuous growth. Let's use a very relatable analogy, a bank account giving you compound interest. If a bank gives you 100% interest at the end of the year, your money doubles. Great. But what if they split it, giving you 50% every 6 months? Because of compounding, you actually end up with 2.25 times your money. Slice the year into 4-month chunks, giving 33% each time. You get 2.37 times your money. Notice how the growth is slowing down? As you slice the year into smaller and smaller continuous chunks, your money grows slightly more each time, but remarkably, it doesn't just grow to infinity. Instead, as those compounding intervals approach infinity, meaning it's happening every day, every second, every millisecond, the growth hits a maximum, invisible ceiling. It fundamentally locks into this very specific, irrational number, 2.71828, and so on forever. This is known as Euler's number, universally represented by the letter E. It represents the absolute mathematical limit of continuous, unhurried compounding growth. It's literally the fundamental base rate of how things naturally expand over time. Section 4. The natural logarithm, nature's favorite base. So let's dive into why mathematicians absolutely love using this specific number E as the base for logarithms. It really comes down to who the math is for. Base 10 is fantastic for human engineers trying to do rigid arithmetic on slide rules or track zeros in a bank account. But base E, which we call the natural logarithm, or ln, is the flowing language spoken by biology, physics, and nature itself. When the universe computes organic growth, it uses base E. Now, don't worry if you haven't taken calculus. The intuition here is actually quite beautiful. When we look at the rate of change, the derivative, for exponential functions, things usually get super messy. For a base of 2, the rate of change is proportional by an ugly constant of 0.6931. For 3, it's 1.0986. But for a base of E, the function e to the power of x perfectly equals its own rate of change. The constant is exactly 1. It is just perfectly clean. So the big takeaway here is that whenever a rate of change in the real world is proportional to the size of the thing itself, like a virus spreading based on the current infected population, or a hot cup of coffee cooling down based on the room's temperature, the natural logarithm and Euler's number emerge out of nowhere as the absolute perfect mathematical description. This elegantly wraps up our journey into E. The number E is fundamentally defined as the one unique number in the entire universe, whose exponential curve exactly matches its own steepness at every single point. The slope of the curve perfectly equals its height. So, as we wrap up today's explainer, I'll leave you to ponder this. John Napier spent 20 years manually writing out tables of logarithms as a clever trick to help sailors divide numbers. But considering how perfectly these abstract curves natively describe everything from the physical structure of our hearing, to the explosive power of earthquakes, to the continuous growth of life itself, did human beings merely invent logarithms as a useful tool? Or did we accidentally uncover the hidden source code of reality? Welcome. I am absolutely thrilled you're here. Let's jump right in. Imagine for a second that we're stepping back through time, just wandering down the dusty halls of mathematical history. Now, today, in this explainer, we aren't just going to stare at some abstract equations on a chalkboard. No way. We are going to trace the fascinating evolution of human thought that gave us literally one of our most powerful tools, calculus. It's this incredible story of absolute geniuses grappling with the impossible and how those very struggles shaped the foundations of our modern world. So, let's kick things off with a bit of a puzzle. How exactly do you measure the speed of a car at a single frozen instant in time? I mean, you look down at your speedometer, right? And it tells you you're going exactly 60 miles per hour right then and there. But think about it for a second. Speed is distance divided by time. If time is totally frozen at a single instant, literally 0 seconds are passing. You can't divide by 0. So the whole idea of an instantaneous rate of change, well, it's actually an oxymoron. It's a massive paradox, and it completely baffled thinkers for centuries. To figure out how we finally solved it, we got to go way, way back. Which brings us to part 1, taming infinity with geometry. Okay, let's dive into this. The journey of this concept is just massive. The ancient Greeks, they were undeniably brilliant, but they were actually terrified of infinity. The thought of a universe going on forever or numbers getting infinitely small, to them, those were horrifying, chaotic ideas. You just didn't mess with infinity. But to solve real practical problems about physical space, they had to find a way to tiptoe right up to the very edge of the infinite without actually crossing over. So we start around 250 BC with Archimedes and his incredibly clever geometric proofs. Then there's this huge historical leap to 1637 when René Descartes brilliantly smashed algebra and geometry together with his coordinate system. And finally, we land in the late 1600s with the incredibly famous and, honestly, quite bitter rivalry between Isaac Newton and Gottfried Wilhelm Leibniz. They're the ones who formalized the modern algebraic notation we use today. But let's rewind back to Archimedes, because he's the one who planted the very first seed. Now, what's really fascinating here is how Archimedes figured out the area of a circle. He didn't just plug numbers into formulas like we memorize today. Instead, he pioneered this brilliant method of chopping a problem up into tiny pieces. Imagine chopping a circle into infinitely small pizza slices. That's step 1. Then step 2, you take those slices and rearrange them. Eventually, they form a shape that looks a lot like a parallelogram. Now, if you imagine making those slices even smaller, like infinitesimally small, that shape becomes a perfect rectangle. So for step 3, you just calculate the area of that rectangle using basic everyday geometry. He was essentially integrating all these tiny pieces together to find the whole, completely avoiding the direct use of those scary infinite numbers. Pure genius. And that brings us right to a major roadblock in our history. Part 2, the paradox of instant change. So while the Greeks laid down this amazing groundwork with static geometry, the world, well, it kept moving, literally. By the 1600s, scientists were trying to track dynamic motion, stuff like the acceleration of falling bodies or the elliptical orbits of planets, and they hit a massive wall. Straight lines and simple geometry just weren't enough anymore. As the mathematician's dilemma goes, change is something that happens between separate points in time. Instantaneous rate of change is actually an oxymoron. This was the ultimate headache of the 17th century. Say you have a curve representing a runner speeding up in a race. The steepness, the slope, is constantly changing. To find a traditional slope, you need 2 distinct points. But if you want the exact speed at one specific point, well, you only have 1 point. It is physically, logically, and mathematically impossible to calculate a rate of change from a single frozen snapshot. But enter our historical heavyweights, Newton and Leibniz. Working completely separately, they both came up with this brilliant workaround to the paradox. You see, a derivative isn't some kind of abstract magical concept. It's really just the best constant approximation for a changing rate around a single specific point. So how did they pull this off? They imagined picking 2 separate points on a curve and then just dragging them closer and closer and closer together. They zoomed in so incredibly close that the curve basically stopped looking like a curve and looked just like a straight line. By doing this, they completely sidestepped the paradox of that frozen instant. They were looking at infinitesimally small nudges in time instead. Now, as calculus developed over time, it definitely shifted away from this visual geometry into the more modern algebraic notation you'd see in textbooks today. But actually visualizing those algebraic rules, that is absolutely crucial for real understanding. It grounds the math back in reality. So instead of just rote memorizing that the derivative of x squared is 2x, try picturing an actual physical square stretching out and gaining tiny new edges of area. Or take a function like 1 over x. You can visualize that as a rectangular puddle of water that's changing its shape to keep the exact same volume. And the sine function? Just picture taking a tiny little physical step around the edge of a unit circle. When you connect all that abstract algebra back to the practical geometry of tiny real-world nudges, the concepts just become deeply, deeply intuitive.
So we've broken things down into tiny rates of change. But what happens when we build them back up? This is part 3, the true meaning of integration. If you ever open up a standard abstract textbook, it's probably going to tell you that integration is about finding the area under a mathematical curve. And yeah, sure, visually on a graph, that's true. But honestly, that's exactly why so many students struggle with it. It just feels so disconnected from reality. Let's look at the practical, real-world view instead. Integration is quite simply the continuous accumulation of tiny bits. Just like Archimedes adding up all those tiny pizza slices, modern integration is really just about adding up tiny, almost constant pieces of a quantity over time or distance. At its core, it's just a summation. And this brilliantly illustrates one of the absolute greatest achievements of the human mind, the fundamental theorem of calculus. It's this incredible realization that the accumulation of a quantity, that summation of bits we call integration, is the exact, perfect inverse of its rate of change, which is differentiation. Think about it. If you know the exact changing rate of a car's velocity, and you add up all those tiny little instances of speed multiplied by tiny little instances of time, boom, you get the exact total distance that car has traveled. The small zoomed-in pieces and the big zoomed-out picture are perfectly linked together. And listen, this isn't just beautiful historical theory. It's the absolute bedrock of our modern world. Part 4, Engineering the Real World. Let's look at how this historical theory translates into a practical method that we use today. Engineers actually rely on a really simple mantra derived straight from this history: chop, multiply, and add. Here's how it works. Step 1, you take a complex, changing scenario and you chop it up into tiny, constant intervals. Step 2, within that tiny, frozen interval, you just multiply the variables together, something like force times distance. Then, step 3, you simply add all those tiny intervals together to get your grand total. It's a method that is honestly as elegant as it is powerful. And this process is exactly how we solve real, practical engineering challenges, totally bypassing the need to blindly memorize complex formulas. We use this chop and add method for all sorts of things, like calculating the total energy needed to pull back a compound bow, where the tension in your hand is constantly dynamically changing. Or we use it to maximize the power generated from solar panels tracking the sun as it arcs across the sky all day. We can even use it to figure out the absolute optimal running path and distance for a basketball player moving dynamically on a fast break. So the crucial point here is understanding how to intuitively apply this. Let's really look at the compound bow example. The physical force gets harder and harder the further back you pull that string, right? So we chop that entire pull into tiny distances where the force feels roughly constant. Then we multiply the force in that tiny interval by that tiny distance, which gives us a small bit of energy. And then we just add all those little bits of energy together to get the total foot-pounds of energy expended. The exact same logic applies to chopping time for solar panels or chopping physical distance into tiny steps on a basketball court. It's the same beautiful concept every time. This is exactly why this summation approach, that whole chop, multiply, and add method, is vastly more effective than what typically happens in a classroom setting. Just memorizing algebraic formulas without truly grasping the core concept, that just leads to massive confusion the second you face a new, novel problem in the real world. But visualizing the concepts, really understanding that you are just summing up tiny bits of data, well, that allows you to recognize calculus everywhere in your daily life. It demystifies the whole subject and turns it from a headache into a real tool you can genuinely use. I have to share this. I absolutely love this quote from Leibniz, one of the primary founders of calculus. He actually said, "I consider these infinitesimals as fictions of the mind, for succinct ways of speaking appropriate to the calculus." That is huge. Even the brilliant minds who literally formalized these rules knew that playing with infinity was just a clever mental trick. These aren't some horrifying literal infinities that we need to be afraid of. They are just deeply clever, practical fictions we use to make sense of a constantly changing world. It really makes the math so beautifully accessible to all of us. Well, that brings us to the end of our historical journey today. But I want to leave you with a bit of a provocative thought, really, reflecting on what we've learned from Archimedes, Newton, and Leibniz.
If the math that governs every major shift in the physical universe is ultimately just an accumulation of tiny, almost imperceptible nudges, how are the smooth, continuous changes in your own life being built right now? Think about it. Every big change is really just a summation of tiny bits added together. It's definitely something to ponder. Thank you so much for exploring the evolution of mathematical thought with me in this explainer today.